Hello my YouTube friends, welcome to this channel. Today we're going to look at bipolar junction transistor AC analysis. I believe that we all are aware what bipolar junction transistors are. Basically, transistor comes from two words, that is to transfer and resistor. So it transfers across resistance. And so the way the transistor operates is basically taking a current from a low resistance level to a high resistance level. And in that case, we call it a transistor, transferring from low resistance to high resistance. And then there are two types of transistors, the NPN and the PNP. So you might be aware of the design. So we're saying if we have a transistor that is pointing in this direction, that is pointing outside the design. So you've got the collector, the emitter, and the base on this side. What we call this transistor is the NPN, which as students at school we used to call this as a short way of memorizing this is it never points in, never points in. That is NPN. And then you've got the transistor that is pointing in like so. So still the same, you've got the collector, the emitter, and you've got the base. So this we used to call it, this is the PNP, which is points in permanently. And that's the way you can memorize these types of transistors. So basically transistors can be used as switches as well as amplifiers. In our AC analysis, we are looking at amplification as the main important aspect of analysis. So join with me as we analyze these transistors and how we use them in AC analysis. So basically what we do in AC analysis is we are aware that you must have some basics in the transistor construction, which must have been covered in our case at CBU as EE220, or you must have looked at DC biasing of bipolar junction transistors as in other books. But in this case, we're looking at analyzing a bipolar junction transistor using of alternating current. And this method of analyzing the bipolar transistor depends on the magnitude of the applied sinusoidal alternating current. Also, the applied AC input may be small signal or a large signal. There are three main methods that we used for small signal analysis. That is the Ray model, which is frequently used. This is what we are going to focus on. And then there's the hybrid pi model and the full hybrid model. And basically these are the common ways that we can analyze a transistor. And apart from employing BJTs for switching, like I mentioned, you can also use it for amplifying signals, which is what we are looking at in this case. So amplification of a signal in a transistor is a bit awkward in a way. A lot of students fail to understand how is this happening, because if we look at it, we've got an AC output signal that is greater than the AC input signal when according to efficiency principles or the law of conservation of energy, efficiency, the power out divided by the power in cannot be greater than 1. But in our case, the reason why this happens is because the power output is obtained from the applied DC power. So it changes the equation here. Instead of us, sorry for that, it changes the equation here. So what we have here, we've got the power input, which is a DC power, and then we've got the power output, which is AC. So this is the whole secret that allows an amplifier to amplify a signal. So more reason why we can achieve that amplification of a signal, as seen in the next slide. So what we have basically is we've got a DC current, a circuit that is a DC supply, a steady state supply of DC current. And the level of that DC current determines the level of amplification. So if we add a control mechanism and we inject in a small signal, a small AC signal, we can achieve a large oscillation of AC depending on the level of DC. So this is the level of DC supply. This is the current DC supply. So the total current then becomes a combination of the DC current as well as the AC small signal, which we've injected into the system from here. And this is how amplification occurs through a transistor circuit. So when we are analyzing the circuit, the peak-to-peak value of the output is greater than that of the input, as you've seen. Then the peak value of the oscillation in the output circuit is controlled by the established DC level. Then you have the attempt to exceed the limit set by the DC level results in clipping of the output at both ends. So what happens is if you try to exceed the DC level, for instance, you've got the sinusoid that is going like so, what is going to happen is going to start what we call clipping. Okay, this is when the wave will clip if we try to force it. That is on both sides. So this clipping can be avoided. You have to set the DC level at a certain level so that you have a normal sinusoidal amplification of the signal to avoid clipping. Okay, and then proper amplification design requires that you consider both the AC and DC components, that they're sensitive to each other and their requirements. And then we can carry out the DC analysis separately, and then on top of that we superimpose the AC analysis on the DC analysis. And so we trying to model bipolar junction transistor, and it begins by understanding what a model is. So in creating a model, we're trying to replace the transistor symbol by its equivalent circuits so that we are able to analyze it in a different way, in a more advanced way. And what a model is basically a combination of circuit elements which best approximates the behavior of a bipolar junction transistor. And of course, there has to be specific conditions for that to occur. And we obtain the model by setting all DC sources to 0, and then we replace the capacitors, or by short-circuiting them. We short-circuit the capacitors. And then we also look at bypassing all resistors in parallel. We redraw the circuit in a more convenient and logical way. So this is the process of modeling a transistor, a bipolar junction transistor. Basically, you earth the DC sources, and then you have the short-circuiting of capacitors, and so on. So we begin by looking at the common emitter configuration, NPN transistor, where you have the input section of the transistor. So you've got the base, the collector, the emitter, and then you've got the base emitter voltage here, which is the same as the base, the input voltage. So the input voltage is basically equal to the base emitter voltage. And the Ray model of a bipolar junction is constructed using these approximations. So we begin at the input side of the transistor. We model the input side, find how the input is going to be, and then we come to model the output side of the resistor. As you can see, the emitter current goes through the forward biased junction, like shown here. When we begin looking at the input side of the circuit, we realize that the characteristics of the input parameters are as shown above, and that is the emitter current, the base emitter voltage, and we've got the voltage here, which is the collector base voltage values. When we get the average of these values, we come up with one curve, which is this one, which is exactly in similarity to the forward bias diode. So we are saying on the input side, the transistor will act more or less like a diode, and in so doing, we replace the input side with the diode. So we replace the input side with a diode, which has the input current being the emitter current and the input voltage being the base emitter voltage. And this is the equivalent circuit on the input side. When we go to the output side, we realize that if we look at the output characteristics that we have, if we maintain the beta to be constant and we look at the different values of the base currents, the characteristics of the output side are such that we can replace the entire characteristic by a controlled current source, or a controlled source which is equal to beta multiplied by the base current, and that is on the output section. And then we can now separate these two, the output and the input section. The diode, afterwards, we replace the diode by a resistor, equivalent, what we call an equivalent resistor, or the resistor equivalent, or which brings about the term the Ray model. And this resistor value is obtained by 26 millivolts over the emitter current. This is the same as the diode resistance, which is the same as 26 millivolts over I, the current through the diode. So its value is obtained from the diode because it's the same behavior as a diode. And therefore, when we come to the input section now, we find that we've replaced the diode by the resistor, and then our input impedance is going to be equal to the input voltage over the base current, which is the same as, because we know the base current is the same as the input voltage is the same as the base emitter voltage. So input impedance is the same as VBE over IBE. But we know that VBE is equal to the emitter current multiplied by the Ray resistance, which is the voltage across this resistor. So it's this current multiplied by that resistance. And we know that that current is a sum of the base current and the collector current that will go through the emitter. So this is the base plus the collector current, and this multiplied by the resistance, which is the Ray resistance. And after manipulation, we find that the input impedance, therefore, is equal to beta plus 1 multiplied by base current and Ray resistance, or equivalent resistance, and then multiplied by the base current. So these cancel out to remain with the input impedance to be equal to beta plus 1 Ray, which is equal to, or approximately equal to, beta multiplied by the equivalent resistance. And so, having found the input impedance, then we have to find the output impedance for us to come up with a model, a Ray model that is going to approximate the behavior of a transistor in this case. So we separate the two. This is the input section. So we have the input here, and then we've got the output on this side. So we know the value of the input impedance. So the important values on this side is the input impedance, the input voltage, and then we've got the input current, which is IB. Here we have the output impedance, ZO, the output voltage, as well as the output current, which is the collector current in this case. So this is now a partial representation of a bipolar junction transistor. But we have to also take into consideration that on the output side, there's additional resistance or impedance that has to be added to complete the model to replace the symbol of a transistor fully. And when we look at it, we've got the output impedance or output resistance, which is RO, which is obtained by the rate of change of the voltage over the rate of change of current. And it can be approximated to be equal to the rate of change of the collector emitter voltage over the collector current, rate of change of collector current. So in short, the transistor symbol is fully replaced by a model. So this transistor symbol, which is the base, collector, emitter, is now represented by this system. So this system now, or this configuration, which is the REM model, represents now the transistor in full. And we can now check its parameters and play with the parameters, because we will now have a model which is clear in terms of parameters, in terms of figures, in terms of how to get the variables. Then we are now able to analyze these various circuits using that model. So if we begin with the collector emitter fixed bias configuration, for instance, and we apply the steps. So to apply the steps, this is going to be grounded. So we zero the DC source, and then if we do that, then the capacitors are short-circuited. So when you short-circuit these capacitances, you basically have eliminated or zeroed the capacitances in this case. And what we remain with is that this section is grounded, and that section is grounded. But then we're able to see that because we have a common ground, this is grounded and that is grounded, we're able to take this resistor, the collector resistor, connected to this output section. And then we've got the RB, the base, which is part of the input section, to remain on the input side. So this is the way our circuit applies. But then we have to now replace this symbol by the REM model. Okay, our REM model. So this must be replaced now by the beta RE and the controlled source, which is beta multiplied by the current. So replacing that, we end up with this model. So RB is maintained. Sorry about that. So this is now the replacement of the model. So we have RB maintained on the input side. Transistor symbol is now replaced by its ray model. So this is the ray model that we've replaced the transistor symbol with. We've got the base current, we've got beta RE, we've got the source, which is beta IB, the controlled source on the output. Then we've got the output impedance, and then we've got the collector resistance. And the current IO, output current, is going through the collector resistor in that way. And we're able to now determine, we can calculate the current gain by knowing the value of the input voltage and the output voltage. Once we know these values, we're able to calculate our voltage gain, which is obtained from these two variables. And we also have to find the input impedance and the output impedance, and then we are able to calculate and analyze or model the transistor. So that is what is happening. If we go from the equation, from the table that you saw, the input impedance then is obtained by looking at the two variables that are parallel to each other here. So we can calculate the resistance. RB is going to be parallel to this resistor, which is beta RE, and that is what you see when you come here. So this is the input impedance. So RB is parallel to beta RE. In most cases, RB is going to be greater than 10 beta RE. And for this reason, we can approximate to say the input impedance is approximately equal to beta RE, but provided that this condition is met. So to use this approximation, you have to verify if this is true. If it is not true, then that applies. And then the output impedance is defined when the input voltage is 0. So when the input voltage is 0, what remains there is that you only have the source becomes 0, and what you have is only RO and RC. So you've got RC there and RO. So the output impedance ZO then is just going to be these two resistances parallel to each other, which is RC parallel to RO, and you obtain your solution in that way. When we come to the voltage gain, like I mentioned, which is equal to the voltage output over the voltage input, this can be calculated from so voltage output is equal to beta VI beta RE multiplied by RC and R parallel to RO. So when we do the calculation of this, and knowing that IB is VI beta RE, we're able to derive that VO can be obtained from simply RC parallel to RO. And this is what we obtain here. And the output is basically can be obtained from comparison of RE. And we can get the gain then for the gain to be equal to RC over RE, provided that RO is greater than 10 RC. So that's the condition. And once we have our voltage gain, then we can understand by how much amplification the transistor is able to conduct and achieve. The common emitter bias example, we'll look at it later on. I'll show you how we determine. And then we'll also look at how we analyze the voltage divider bias and how we solve the voltage divider bias. In short, what happens with the voltage divider bias, you've got two resistances in the input side, which have to be obtained as a common or equivalent resistance R, and this is what we obtained here to obtain one resistor, and that resistor becomes parallel to beta RE, and then the RC stays the same on this side, and the calculations are basically the same. Look at that example also shortly. And then we've got the emitter resistor, the common emitter bias configuration model. In this case, you've got the configuration and the equivalent model as shown. Configuration and the equivalent model shown as below. So this is what you are going to obtain. In this case, you've got the RE resistor, that is the emitter resistor, replaced in the circuit, and it has to be considered in that circuit. So it has to be inserted and the calculation considered like so. So that an example, a good example of you can see it on, let's say, example 5.3 boiler stud. You can go through that on your free time. In the next video, I'm going to look at the two examples that I've shown, and then I would like the students to go through the analysis, that is the using multisim to run the analysis on your own using multisim, which I think I've introduced to you, and you can go through it, do your own analysis, and obtain your results for a voltage divider bias. And you can submit that to me via email or via our group on Edmodo. Kindly also consider the emitter follower configuration and the example 5.7 in boiler start. You can go through that in your free time. And so the next video, we're going to look at the examples. Thank you for your attention. Thank you.